Hello, and welcome to Alkenes, the third video in this series. Alkenes are the hydrocarbon chains that possess a double bond. You should remember that alkanes have the formula 2n plus 2, where n is the number of carbons and the total is the number of the hydrogens. Since alkenes replace two of those hydrogen bonds with a carbon-carbon double bond, their formula is simply 2n. Last video, we also touched on the idea of saturation, where a molecule only has single bonds. As alkenes have a double bond by definition, they are always unsaturated. But here's an important question. What is a double bond? By answering it, we'll also get a good idea of why alkenes can have very different properties to alkanes. To understand a double bond, let's first look at a single bond. Single bonds are formed by the overlapping of areas of electron density between the s orbitals of two atoms, and we can draw them like this. We call this a sigma bond. You may be tempted to think that a double bond will be two sigma bonds, but you would be unfortunately incorrect. For a double bond, we take a single bond and add on a completely different kind of bond, a pi bond. A pi bond is formed by the interactions between two p orbitals. Those p orbitals are dumbbell shaped and look like so. What having two p orbitals on either side of the sigma bond does is that it creates an area of electron density above and below the sigma bond between these pi bonds, which we can show with dashed lines on either side. We call this a pi bond. Therefore, a single bond is a sigma bond, but a double bond is a sigma bond and a pi bond. In our first video, we mentioned that stereoisomers matter for molecules with double bonds because double bonds are not free to rotate. The nature of pi bonds is why. They must be aligned like this, and any rotation of the carbon atoms would require breaking the bond. As a result, having a double bond will lock that part of the molecule in place. So, as always in chemistry, we really care about areas of electron density, and so do certain molecules. There are some reactions where a sigma bond doesn't have enough electron density to cause a reaction, but a sigma bond with a pi bond does. This is the key to the unique reactive properties of alkenes, and we call the molecules that love the electron density that an alkene's double bond can provide electrophiles. Electro stands for electron and means negative. Phile means that it is attracted to that thing. Electrophiles are really important to us because when electrophiles are present, alkenes can undergo what we call electrophilic addition reactions. You need to know quite a few of these, so let's go through them. Firstly, so long as we have a nickel catalyst, we can easily turn alkenes into alkanes by adding some hydrogen, which would replace the carbon-carbon double bond with a carbon-carbon single bond and two carbon-hydrogen bonds. The specification would apparently like you to know that this is important for manufacturing margarine from vegetable oils, which is bizarre and ominous, but interesting trivia nonetheless. Using the same idea, but without the need for a nickel catalyst, we can break the carbon-carbon double bond and add two carbon-halogen bonds the same as we could hydrogen. This also works with bromine and iodine. As the product, has two halogen atoms and no double bonds, we call it a dihalogenoalkane. For our third example, we can do exactly the same thing with a hydrogen halide to instead add just one halogen atom and one hydrogen atom. We call this product a halogenoalkane, and our next video will be all about them. There are two final electrophilic addition reactions with alkenes that you need to know about. These ones also involve oxidation. Firstly, we can add steam, and it must specifically be steam with an acid catalyst to an alkene to create an alcohol. But secondly, if we want to oxidize that alkene even more, we can add that alkene to acidified potassium manganate 7, an extremely potent oxidizing agent. The acidified part provides the hydrogens, while the potassium manganate provides the oxygens. Because the potassium and manganate do not actually react though, they are technically catalysts and we do not write them in the reactions equation. But they are still supremely important, and you must bury into your memory that an alkene plus acidified potassium manganate 7 produces a diol, a molecule with two OH functional groups. Those were 5 examples of electrophilic addition reactions, which at A level you are expected to be able to draw the mechanisms for. How do we do that? Well, first let's go over a few basic concepts: electron lone pairs, heterolytic fission, and curved arrows. Firstly, heterolytic fission is the other type of bond fission to the homolytic fission discussed in the previous video. It is where, when a bond breaks, both electrons in that bond go to the same atom. For these mechanisms, we show this transfer by drawing curved arrows. Let's take a super basic example. Here, a positively charged hydrogen ion is attracted to the area of electron density around the silver bond. We can mark that area of electron density with a delta minus. In this reaction, the hydrogen ion attracts one of the electron pairs in the double bond to instead form a bond between one of the carbon atoms and itself. Again, we show the movement of an electron pair with a curved arrow, like so. Always from the bond to the species those electrons are going to. Then, for the product of this reaction, we show that a bond has formed here. And you'll also notice that the product is still positive, because the double bond has broken, and now this carbon atom on the right has only formed 3 of the 4 bonds it needs to be stable. Therefore, if a nucleophile were to come nearby, that would then react, as one of these electron lone pairs would help form a bond here. And so we would get an alcohol. Notice how the lone pairs on this oxygen atom were shown with a pair of dots. You now have a basic understanding of how we draw mechanisms. So now let's finally draw one of the electrophilic addition reactions we mentioned earlier, an alkene plus a halogen. In this case, we'll go with ethene and bromine. Firstly, we need to write the displayed formulae of our reactants, like so. Secondly, we note the area of electron density around the ethene's carbon-carbon double bond with a delta minus. At this stage, you may be wondering what makes the bromine molecule electrophilic when it has no charge and is completely nonpolar. The answer is that the electron density around the ethane double bond repels electrons in the bromine molecule, shifting them away and creating another area of electron density over here. But wait, if this is delta minus and there's more electrons here, that means there's less electrons here, making this delta positive. This next step is now identical to the example we had at the addition of hydrogen. The delta negative double bond attracts the delta positive bromine atom and the double bond breaks, causing the electron pair that form that double bond to be given to the delta positive bromine atom and form a carbon-bromine bond. But hold on, bromine can't form two bonds. That means that the bromine-bromine bond needs to break. And that means that the electron pair here in the bond will go to the delta negative bromine atom. That's all we need to do to annotate this first stage of the reaction. Let me show you the next one now. As shown by the two dots, we can see that there is a negative bromine ion with a lone pair of electrons and also a positively charged carbon atom missing a bond. Almost needless to say, they are attracted to each other. We draw another curly arrow from the electron pair to the carbon atoms to show where that electron pair is going. And then we can add another straight arrow to point us to the next stage of the reaction, the final product, which is a single molecule of 1,2-dibromoethane. We really nailed that. Let's finally go over one last example for when we instead have a hydrogen halide and an alkene. Again, let's first mark the double bond as delta minus before looking at the electrophile. Last time, the double bond induced polarity into the molecule that became our electrophile, but in this case, Hi is already polar, as iodine is more electronegative than hydrogen. So let's mark on a delta plus and delta minus immediately. The delta minus double bond then attracts the delta positive hydrogen atom, and the double bond breaks with an electron pair migrating to form a carbon-hydrogen bond instead. And then the hydrogen-iodine bond also severs as a result, with an electron pair migrating from that bond to the iodine atom. Moving on to the next step, we are again left with a negative ion that has a lone pair, as well as a molecule with a positively charged carbon atom. They, of course, bond together, giving us the final product of 2-iodopropane. However, this is not the only product that this mechanism could give us. If we go back to the second step of the mechanism, what if, when the carbon-carbon double bond broke, it was the other carbon atom here that bonded with the hydrogen? Well, we can write a reaction for that too, and follow it all the way through. And in that case, we're left with the product 1-iodopropane. So, which of these reactions actually takes place? The answer is that both do, but the more stable product is formed more than the less stable product. We call the more stable, and therefore more abundant product, the major product, and the less stable, and therefore less abundant product, the minor product. So which is which? Well, put simply, we care about the carbon atom that the hydrogen ends up bonded to, which would be these ones. The more bonds to other carbons that these carbon atoms have, the more stable the molecule. This carbon atom is only bonded to one carbon atom, so we call this species a primary carbocation. This carbon atom is bonded to two other carbon atoms, so we call this a secondary carbocation. And if we had a species of an atom that was bonded to 3 other carbon atoms, we would call that a tertiary carbocation. So, as tertiary carbocations are more stable than secondary ones, and secondary ones are more stable than primary ones, we know that the secondary carbocation will be our major product, and the primary one will be our minor product. Congratulations, that's electrophilic addition mechanisms covered, at least as far as how to write them for the rest of this video. We can now, at last, move on to other things, like the most important qualitative test for distinguishing alkenes from alkanes. You should remember it from GCSE. Bromine water is orange, and if we add a saturated molecule to it, like an alkane, its colour will not change. If we instead add an unsaturated molecule to it, like an alkene, it will turn colourless and react. This is an example of the halogen electrophilic addition mechanism we covered 6 minutes ago. Keep this test in your repertoire, as many questions in the organics topic are about identifying different organic molecules through testing. Another thing you should remember from GCSE is polymerization, a reaction that alkenes can undergo where they break their carbon-carbon double bond and link up to other identical alkene molecules that have done the same. This creates a long chain of a repeat unit, and you must be able to identify the repeat unit of an addition polymer when given the monomer, as well as vice versa. For example, how do we find what repeat unit we would get if we use this as the monomer? Well, first we've got to break this double bond. That leaves us with this molecule where the carbons here each only have 3 bonds when they want 4. So they bond to the carbons in other alkenes that have broken the double bond. From here, the last step is just to rearrange what this looks like, so that we have the bonds to other carbons running horizontally. Then we can just add brackets around and an N to show that this repeats. Now let's try and find a monomer from a small segment of a polymer. First, we just got to identify where this repeats and where the carbon bonds that are going to break are. In that case, this is the repeat unit. We can draw that out quickly and get our monomer, except we also have to re-add the double bond, which would be here. And it's that straightforward. We have an alkene again. So that was about how we get polymers, which in turn are used in plastics, some of the most useful and revolutionary materials in the world, because they are so strong and so ridiculously cheap to produce. Unfortunately, we also have to dispose of these polymers eventually. Here are the 3 ways that we do so. The first is recycling. Some, but not all, polymers can be broken down and remolded into different shapes for reuse. A process relatively small on energy costs that is far cheaper than forming new polymers. The second is incineration, something common for polymers that are for all intents and purposes worthless, often due to their inability to be recycled. One small positive of this is that incinerating polymers can release energy that we can collect. However, a larger downside is that there are many polymers, including PVC, that contain harmful elements like chlorine. If they are incinerated, they release these elements as gases. And for perspective, chlorine gas is so deadly that it was used as a chemical weapon in World War I. The third And final thing we can do with waste polymers is crack them out of being a long chain and back into smaller molecules that there are a lot of potential uses for. Exactly the same as we would crack alkenes to get smaller alkenes. For the very final point on the specification that we're going to cover in this video, what can we as chemists do to limit the problems disposing of polymers can create? There are two main points. The first is that in an ideal world, we'd be able to create way more biodegradable polymers. That way, we do not have to worry about disposing of them through methods like incineration. However, biodegradable polymers are by necessity not so suited for long-time use, and different biodegradable polymers require different specific means of disposal, which can be expensive. And then the other point is simply to be more careful with our incinerations. The chlorine gas is not so bad if we have well-equipped facilities to deal with it. Thank you for watching. That was video 3, and video 4 we're going to cover halogen alkenes. See you there.